Hi guys, so today we will so today we will continue our adventure with the determinants of matrices, and just like I said, we will also talk about elementary matrices in more detail, as well as about the LU factorization. By the way, if you guys feel like you can be more vocal now, there are only 13 people here. So I would like to continue. So last time we talked about about determinants of triangular matrices, and I want to give an example. So the example that I have in mind, so the example number 6 from the notes. So how to compute compute the following: the determinant of the matrix of the following matrix. A is 2, 0, 0, 0, 4, negative 2, 0, 0, negative 5, 6, 1, 0, and the last 1, 5, 3, and 3. Okay, now I want you to look at this and to tell me what kind of matrix is this? When you look at it.
Lower triangular.
Say that again.
Lower triangular.
You said upper triangular?
Lower.
Lower triangular, right?
Triangular.
Say that again. Who?
Yeah, lower triangular.
Lower triangular matrix, right? The lower triangular matrix. And we said that based on our previous consideration, as you can see, the formula above, we said that the product, the determinant of A, is nothing else than just the product of the elements on the main diagonal, right? You see them here. Look at them. Right? Okay. So in other words, this will be 2 times negative 2 times 1 times 3. And this will give us negative 12. And that's it. So once again, either you have like a lower or upper triangular matrix, it doesn't matter. The determinant of that will be the product of the elements on the main diagonal. Okay.
So all the numbers all the numbers have to be 0 on the upper and lower depending on which it is.
Or lower, exactly. Exactly, that's what it means. So you see all these numbers here above the diagonal, right, are 0, right?
Mm-hmm.
Or you can reverse it, right? You can say like, if I have all these numbers below the main diagonal are 0, then that's it. The determinant will be the product of the elements on the main diagonal. Okay, now let's talk about determinants and elementary operations, because I want to veer towards properties of determinants. So I think this example is clear. So we'll talk about determinants and elementary operations. In this way, what we want here, we want basically to use this use elementary raw operations to evaluate the value of a determinant, or maybe not just use only raw operations. We can also use column operations to evaluate to determine the value of a determinant, or maybe even more, maybe we can recognize some kind of conditions which will give us, which will yield that the determinant of the matrix is 0. So we'll deal with that. And pay attention, I want to stress this out right from the beginning. When we will do, when we want to compute the determinants of matrices, we will do the same type of elementary operations that you have been used to, that you did for systems of linear equations and so on. But this time, for determinants, we'll have one advantage. We can also perform the same type of operations to the columns, not just the rows. So pay attention to that. That's a huge advantage. And I'm going to start with one of them. The first one I want to talk about is, let's say, about determinants and elementary row operations, just like in the title, and elementary row operations. And I want to stress this, we're going to perform on row. So let me give you an example. Let me ask the following questions, just like in the notes. Which of the following determinants is easier to compute? So let's take the determinant of this matrix. So I'm going to write it like this. Let's say it will take a 1 negative 4 by 4. So it's 1 negative 2 3 1, 4 negative 6 3 2, negative 2 4 negative 9 negative 3, and the last row will be 3 negative 6 9 and 2. So the determinant of this matrix, if you look at it, there is not a single 0 there, which it's kind of inconvenient for me if I want to do like a row or column expansion. Or let's take an easier one, the determinant of B, which will be this: 1 negative 2 3 1. The second row will be 0 2 negative 9 negative 2, 0 0 negative 3 negative 1, and then 0 0 0 negative 1. Well, I think the answer to this question is quite obvious, right? It's quite obvious, the fact that it's easier to compute the determinant of the matrix B, right? Well, guess what? What if these two matrices are basically the same? So, but first, let's compute the determinant of B. What is the determinant of B? Can you tell me? First of all, what is the matrix B? How does it? Do you recognize it based on what we have? But based on previous considerations.
Upper triangle.
So this is what we call an upper triangular. So the determinant will be what? 1 times 2 times negative 3 times negative 1, which will give us 6. Correct. Now, if you want to compute, oh my goodness, based on row expansion or column expansion, the determinant of A. So let's do it. In fact, I will just do it quickly. So let's suppose we expand over what? Over the first, on the first row, right? Let's look at this here. So when we want to compute this determinant, we're going to do first row expansion. So when we do this, we're going to get the following. So let's write it. So this will give us, so this will be 1 times, I forgot to say, negative 1 to the power 1 plus 1 times the minor, right? M11, correct? This is just the cofactor 1, 1. Plus -2 times -1 to the power 1 plus 2 times M12. Again, this is C12, the second cofactor. Plus, now let's look at the third one. So it will be 3 times -1 to the power 1 plus 3 times M13. And guess what? The last one will give us, will be -1 times, wait, I want to be, no, it's 1, I'm sorry, plus 1 times -1 to the power 1 plus 4 times M14. Oh, M14. So these are the minors, right? And by the way, this is the cofactor C13, and this is the cofactor C14. Well, I can write this as the first one will give me M11 plus, and minus 2, in fact, plus 2 M12 plus 3 M13 plus, minus M14. And now we have to compute these guys, so let's write them down. M11, in fact, I will just write them. So this will be -6, 3, 2, right? Then the second one will be 4, -9, -3, and -6, 9, and 2. The M12 will be the second minor. So again, this will be 3 determinants of 3 by 3 matrices. So it's 4, 3, 2, -2, -9, -3, and 3, 9, 2. Man. M13 will be, so if we look at the matrix, it will be 4, -6, 2. Then we have -2, 4, and -3, and 3, -6, and 2, right? And the last one, M14, will be 4, -6, 3, -2, 4, and -9, and 3, -6, and 9. Okay, so these are the 4 minors. Good luck with computing these. Whatever, I will leave it to you as an exercise to compute each and every one of them. The first one is, I don't know. So I'll leave it to you as an exercise to compute all of them, all minors. And guess what? After you compute all minors, the result will be the same. And so the determinant of A, so I'm going to leave these details to you. So after we compute the minors, the determinant of A again will be 6. Wow. So the determinant of A is the same as the determinant of B. But the way we computed determinant of B was very unpractical. Do you see how hard this is to compute in this way? Oh, my. So the moral of this example is try not to do this. This is the super hard way. Well, when you have your exam, it's going to be like a 24 hours exam, so you can do whatever you want. But for you, to be more practical, maybe there is a way of reducing the matrix A to the matrix B so that we can compute the determinant directly without giving or without computing all these minors and having all these headaches. It's not going to be as, because it's quite painful to compute all this. So we'll see. We'll get back to this example, but before we do this, let me give you some other examples, maybe easier ones. So example number 1. So we want to see what kind of effects we have on elementary row operations of a determinant. And the first thing that I have in mind is the following. Let me interchange 2 rows in a matrix. So in other words, so once I do these elementary operations, I want to answer this question: how this will affect its determinant. That is the question. So I'm interchanging 2 rows in a matrix. I want to see what happens to the determinant. Okay, let me take this matrix A, and I want to compute. So it's, let's say, 2, -3, and 1 and 4. Okay, so this is the determinant of this. It's quite easy to see. That is what is 8 plus 3, which is 11. And now what I'm going to do, let me consider the matrix B. I'm interchanging 2 rows, right? So I'm interchanging row 1 with row 2. So I'm going to do it like this: 1 and 4, and 2 and -3. What do you think is going to happen? What is the value of this? Well, yes, I mean, here
-11.
is -11. So if I'm interchanging 2 rows, maybe the value of the determinant will be a negative. Okay. Let's give some other examples. Let's see. Let's do some other elementary operations. Let's say multiplying a row. Multiply a row by a non-zero constant. So we want to see how this will affect the determinant. The same question. How this will affect the determinant. Okay, let me give you an example. Let me take matrix. Let me take the determinant of this matrix. Again, a 2 by 2, 2, -8, -2, and 9. Okay, what is the value of this determinant?
2.
2, correct. And now what I'm going to do, I'm going to multiply by a non-zero constant. Let's say I will multiply. So let's say the matrix B is obtained from the matrix A by multiplying the first row, and pay attention here, first row, only the first row by, let's say, non-zero constants, let's say 1/2. It's very convenient for me. And now let's see, so this will be the first row, only the first row, pay attention. So it will be 1 and -4, -2 and 9. And the determinant of this will be what? Will be 1. Look what happened. So I have half of the value of the determinant of A, correct? Okay. Let's let's take another naive example. So far, you can infer some what happens, but let me take another innocent example. Let's say,
So I have a quick question.
yes.
Yeah. So that 1/2, is that just an arbitrary number, or where does that
Yeah.
1/2? How did you?
I just took 1/2. But you can take 1/3, 1/10. It will happen the same thing.
Thank you.
So I just took 1/2 because I want things to just to simplify nicely. So this is why I took it. Okay. By the way, who has the question? Huh? Because I would like to get to know you more. So if anyway, okay. So let me take another innocent example. Let's say if I multiply. So with the third a row by a non-zero constant, and add it to another row. Wow. Let's see. Let me take this matrix, the determinant of the following matrix. So it will be 1, -3, 2, and -4. So the determinant of this guy will be what? 2, right? Yes, 2. Okay. And now what I'm going to do is the following. So the matrix B is obtained from the matrix A, by adding let's say -2 times, okay, let me write in words, times the first row of A to the second row of A, to the second row of A. Okay, so that's my matrix B, so let's do it. So let's see, it will be the determinant of, I said that is -2 times row 1 plus row 2. So it will be what? 1, -3. And now the second row will become what? 0 and what? And 2. What is the determinant of this? 2. Ooh, is the same. You see, these are just very innocent examples. And now I would like to give you the theorem, which confirms your expectations. And the theorem says the following. So this theorem will concern the elementary row operations and determinants. Okay. So now let's consider, let A and B be square matrices. It doesn't matter, let's say of order n. And now we have the following. The first, we have 1. When the matrix B, when B is obtained from A, by, and pay attention here, interchanging two rows of A, then the determinant of B will be negative determinant of A. Okay. The second one, when the matrix B is obtained from A by adding a multiple of a row of A to another row of A, so adding a multiple to another row of A, then guess what? The determinant will be the same. So determinant of B is equal with the determinant of A. Okay. And now the last one, the third one, when the matrix B is obtained from the matrix A by multiplying a row of A by a non-zero constant, then guess what? Then, let's say a non-zero constant, let's call it C, then the determinant of B is nothing else than just that constant times the determinant of A, right? Also keep in mind these. So C is a constant. Okay. So these are the properties, the three properties that you need to know for determinants of matrices, and we'll see some examples how we can find the value of determinant instead of doing all this row expansion, column expansions, and so on. You can just apply these kind of elementary operations. So let me give you an example, and we'll do it together. Example. So I want to find the determinant of the following matrix. A is, so we have a 3 by 3, so it's 0, -7, 14, 1, 2, -2, and 0, 3, and -8. Okay, let's, I want you to look at it for a minute or two. And maybe we can perform some elementary operations. So we want to compute the determinant of A, right? So we have this. So let's 0, -7, 14, 1, 2, -2, 0, 3, -8. And we want to play with some of the elementary operations. What would you suggest? For example, let's interchange the first two rows. So the first thing I want to do is interchange the first two rows. So I'll get negative, right? 1, 2, -2, 0, -7, 14, 0, 3, -8. So what I did here, let me write it. Interchange the first two rows. So that's what we did. So this is so row 1, row 2, and row 3. So we interchange row 1 with row 2, and we based on the property. Let me go back. You see it here. Property number 1. When B, we said that when B is obtained from A by interchanging two rows, then the determinant will be a negative. Okay, so this will be negative. And all right, let's see, what other operations would you suggest to do? Maybe we can do, so let me explain you the goal. The goal is that I do this elementary operation so that at some point my matrix will become an upper or a lower triangular matrix, so the determinant is quite clear. So what would you suggest? If you look at this, can I do something?
You could multiply row 2 by -1/7.
Exactly. So exactly, or I can factor out. Yes, exactly. I multiply by 1/7, or I can factor out 7. So I'll have 7 times 1, 2, -2. Here I have 0, -1, right? Wait. So I factored -7. Sorry. So here I have 1. So I factor -7, and here I'll have -2, right? And the last one will be 0, 3, and -8.
Are you factoring
Okay.
out -7 or -1/7?
No, what Liliana said, like I can divide by 1/7, but I can factor 7 here, you see? Look here.
Oh,
so if I factor -7, I'll have a -7 right in front of it, times the negative will be 7. And then is it clear now?
Yeah, it's clear now, I see it.
Okay. All right, what to do next? What do you think I should do? Keep in mind, I want my matrix to become at some point upper triangular. So the only thing that gives me some problems here will be what? Will be this guy here, this 3 here, right? So I need to do something about it. So what should I do?
R2 by -3, and then add that to row 3 to get a new row R3.
So you say add, you multiply -3 by this to the second row, right? By the second row. Yeah. Exactly. So we need to multiply -3 to the second of the, to the second row, by the second row, and then add it to the third row, right? Okay, let's write this. So multiply -3 times okay, second row, and add it to the third row. All right. In other words, we'll get the following. So this will be will be what? Will be, let's not forget we have the 7 here. So it will be 1, 2, -2. And then it's the row. So 0, 1, -2. And the last one will be 0, 0. And the last one is -2. Right? What do you think about this now? Can you see something about this matrix?
Yeah,
You see?
becomes upper triangle now.
It's upper triangular. So all these guys below the main diagonals are 0. So this is upper triangular. Well, since we've talked about the determinant of upper triangular matrix, so this will be equal to 7 times 1 times 1 times -2, which will give us -14.
-14.
Well, you can try I would leave it to you as an exercise to do it in a traditional way, just like expand this. Okay, just look at the matrix. Just expand on this. You actually can do it easy. Now that I look at it, you can just look at the first column. You can expand it on the first column here, right? You write the minors. The only thing you need to compute it will be this guy here, the minor of this. So it will be quite easy. In fact, it's easier than I thought. But anyway, okay. There will be another example. In the notes. So, and in fact, I will just remark. So just like I said, although the previous theorem is stated in terms of elementary row operations, the theorem remains valid if you do also, instead of row, you do the column operation. So the previous theorem stays true if we replace rows with columns. So it's the same thing. And instead of saying, so row operations, you do the column operations. It's the same thing. By the way, I want to stress this. This will be equivalent only when you want to compute the determinant of the matrix. I want to make myself very clear. Column operations. So it doesn't matter which one you want to perform. If you don't like the rows, you can do the same thing with for columns. The value of the determinant of the matrix will not change. And there is an example which I'm going to skip. I would like you to see the example from page. So see the example from, well, it depends. Page, it's 19 or 96, whatever you want to call it. 19, 20. Okay. Now I want to talk about matrices and zero determinants. So matrices and zero determinants.
I have a question before you move on to that.
Yes, okay.
Basically on your page 96, on the following, like right, or going to the next page 97 on that example,
Okay.
the second column, they all turn into zeros. Would you mind explaining how only the second column was able to turn into zeros?
So you see that the first two columns are multiple of each other? Right? If you look at that, look at the first two columns, right? Okay, in fact, let me write the matrix. Since you asked, why not doing it? So let's so the example, we want to find the determinant. So let's consider this matrix. -1, 2, 2, 3, -6 and 4, 5, -10 and -3, right? Let's look at the first two columns. Look at this and look at this. What do you see?
Okay, yeah. If you multiply times.
If you multiply, right? If you multiply column number 1 by, so this is, let's say, C1, and this is C2, right? If you multiply column 1 by 2, you'll get by -2, right? So C2 is -2 times C1. Agree with me?
Yes, sir.
Okay. So once you do this, well, you can obtain a column of 0 by just adding 2 times the first column, right?
Yeah.
To the second column, because you observe this, and then you'll get some zeros. And then when you get the column of 0, it's easy to do, so to proceed further. Is that clear?
Yes, sir. Yes,
Okay.
thank you.
Anyway, I will let you look at this example in the notes. It's not hard to see. And now let me veer towards matrices and zero determinants. You will see that there is a there will be some way of doing elementary row operations or elementary with columns, which will allow us to obtain matrices with zero determinants. So in other words, we want to see under what conditions we obtain matrices with null determinants. Why is this important? Well, it will be important when, for example, I would like to compute, let's say, the inverse of a matrix. Like I mentioned in my previous lecture today, I cannot compute the inverse of a matrix unless I know that the determinant of that matrix is non-zero. So in other words, I need to avoid that. So it's good for me to know under what conditions I have matrices with zero determinants. And we have the following theorem. Which says the following. So basically, I will just say it. Conditions that yield a zero determinant. This is very important. Okay. If A is a square matrix, of order n, let's say, and any of the conditions below is true, then the determinant of A is 0. So if one of the conditions that I'm going to mention is satisfied, then the determinant of the matrix is is 0. And the first condition is the following. Let's say an entire row or column. So like I said, when I'm talking about rows for determinants, I'll also talking about columns as well. An entire row or column consists of zeros. Consists of zeros. So if I have a row or a column which is 0, forget about it. The determinant will be 0. Another one. 2 rows or columns are equal. 2 rows or columns are equal. The third one, 1 row or column is a multiple of another row or column, of another row or column. Guess what? If I want to go, so it's a multiple of another row or column. So guess what? If I want to go back to this example, can you tell me what is the determinant of this matrix by just without doing anything?
0.
0. And so determinant of A is 0. Immediately. You don't even need to do anything. So I want you to look at these conditions. So this is the theorem. Under these 3 conditions, we will have a matrix with the 0 determinant. If you notice any of these conditions when you try to compute the determinant, or after you do some elementary row or column operations, then you can stop. It's just the determinant is 0. For example, let me do some examples. For example, let's see. Before I even go and talk more about properties of determinants, let me do a quick example. Okay. So example. Find the determinant of A of the following matrix: -3, 5, 2, 2, -4, -1, -3, 0, and 6. Anyway, this is a 3 by 3 matrix. It's a square matrix. It's not hard to find a determinant. But, you know, by using the traditional approach with the minors, by just expanding over 1 row or 1 column. But let's forget about that for the moment, and let's use the properties that we have learned so far. So I want you to look at this matrix. So I want to compute the determinant of A. I want you to look at it and tell me what you see. Is there something that you see about this? What do you think? What do you see? Do you see something? For example, you see a 0 here, right? Keep in mind what you want to do. You want to create as many zeros as possible. So is there a way for me to create another 0 somewhere?
Yeah, if you multiply 2 times the first column.
Say that again.
If you multiply 2 times the first column and add it to the third row or third column.
Pay attention. Okay. I want to make myself clear. When you do operations with columns, we just stay with columns. When you do operations with rows, you stay with rows. Don't multiply. But okay. So you multiply. You say you take the first column and you multiply what?
You multiply 2 times the first column and add it to the third column.
But do I get any zeros?
Yeah, the 6 is gonna go to 0.
So you multiply. Okay. So you take the first column. Okay, I see. You take the first column here, C1, right? And you multiply it by 2, correct? And you add it to the third column. All right, let's do it. Let's do it this way. So we'll have the following. So first, let me write the matrix again. So that we see it. 2, -4, -1, -3, 0, and 6. And you say now, what I'm going to do will be the following. So I'm going to multiply 2 by first column and add it to the third column. So everything will stay the same. So let's look column wise now. 5, -4, 0. And now 2 times first column. So it will be 2 times -3, -6, plus 4 is -6 plus 2 is -4, right? Then I will have here 2 times, okay, 2 times 2 will be 4, so it will be a 3. And now it will be a 0. Perfect. Right? So the determinant will stay the same. All right, great. But what can you do now? You have 2 zeros. You see, when you have 2 zeros, you are lucky because look, I can expand over this the third row, right? If I do the if I expand, so I can do
Shouldn't that be negative?
expand. Say that again.
Shouldn't that be -3?
Yeah, it's -3 here. You mean here? It's -3.
The third number on the second row.
Here, this one?
4. Yes. Shouldn't that be -3 since it's
No.
the
no,
negative? Oh, okay.
No,
Never.
it's 3. It's 3. It's correct. And now I can expand on the third row. Okay. And now I will leave it to you. In fact, this will be easy. Let me just write it quickly. So this will be -3 times -1 to the power 3 plus 1 times the minor, which will be 5, -4, -4, and 3. And this is easy to compute, so it will give you 3. Okay, and that's it. All right, so this was an easy example, but I can cook up other examples. For example, let me give you some monstrosity here. So yes, yes, Blake.
Could we do another row operation, or if we do, can we do like
Such as
by the top row by a -1 to get rid of that bottom 3? Would that not work? Turn that -3 into a 0.
Can you say that again?
So if we multiply the top row by -1, should we get rid of that?
Okay, multiply by -1 and add it to the third row, right?
Yes.
Yes, it's the same thing.
Okay.
You can do that. Try to see if you get the, in fact, try to look for another operation, row or column operation, that will give you, and you'll see that the value, try to see if you get the same value. That's very interesting to play with these properties. All right, another example, we want to find the determinant of the following matrix. Man, this is a big one. Oh my. So it's a 5 by 5. 2, 0, 1, 3, -2, -2, 1, 3, 2, -1, 1, 0, -1, 2, 3, 3, -1, 2, 4, -3. And now let's see the last row. 1, 1, 3, 2, and 0. Okay. Ouch. Oh, whoa. What did I do here? So this is, okay. So this is the matrix. Look at it. It's a 5 by 5 matrix. If you want to expand over a row or a column, I would not suggest doing that. Well, you can try. You can do it if you want to, but trust me, you will be suffering. So you don't want to do that. So maybe you can do something else. Maybe try to, I don't know, cook as many zeros as possible. In fact, if you look at it, I want you to look at it. Look at it for a minute and tell me what you think. Do you see something in particular about this matrix when you look at it?
You can turn the last two, or on the second column, you can the -1 and the 1, you can turn them into zeros.
Aha, you see, if you look at the column, wait. If I look at the second column, right? C2. Maybe I can do something so I can turn that into zeros, right? Well, so what should I do? What do you think? You see, I have here a -1, I have 1, so I have a bunch of options. So I can create some additional zeros, right? So how can I do that? Well, I can add the second row to the fourth row, correct? Right? Just look at the second row here.
Yeah.
And I can add it to the fourth row. So, and the determinant, and then I can add I can multiply the second row by -1 and add it to the fifth row. So I can do two operations at the time. But anyway, so the determinant of A, so let's write this down. The determinant of A will be So let's write the, oh my God, it's gonna be painful to write this matrix. It's gonna, oh. So we said that we want, let's do it step-by-step operation. So we said that we're gonna add the, so let's 2, 0, 1, 3, -2. And by the way, I have to tell you a secret. I really hate computations, but anyway, what can I do? And -2, 1, 3, 2, -1, 1, 0, -1, 2, 3. And we said we're gonna add the second row to the fourth row. So we're gonna have 1, a 0, 5, 6, and -4. Okay, 1, 1, 3, 2, 0. Okay. Now, what can I do now? Can you tell me? Okay, I forgot to say this is the determinant of this. Not the matrix, is the determinant. Okay. What else can I do? Can you tell me? Maybe I want to create more zeros. So what else can I do so that I have more zeros?
Multiply row 2 by -1, and then add it
And
5.
to the fifth row, okay? So we're gonna have the following. 2, 0, 1, 3, -2. -2, 1, 3, 2, -1. The third one is 1, 0, -1, 2, and 3. 1, 0, 5, 6, and -4. And the last one is, and now we said we're going to multiply -1, right? So we'll have what? -1 row 2 to add, so it will be 3, 0, 0, 0, and what?
1.
1. And now at this point, you look at it. Look at this column. You only have one non-zero here. So we can easily compute the determinant of this. So this will be equal to what? All of them are 0. So you'll have 1 times -1, what power? That's what the position is at. So 4 times, it's minor. So it will be a 4 by 4, 2, 1, 3, -2, 1, -1, 2, and 3, 1, 5, 6, and -4, and 3, 0, 0, 1. And now you can do the same thing with this. Again, you can apply the operations and you can still reduce it. So I'm going to leave it to you as an exercise to finish it off, right? Now you look at this row here, right? You can expand by this row, or you can do more elementary operations and so on. All right. I don't want to lose too much time with this, since I want to talk about properties of determinants, and unfortunately I cannot cover the LU factorization and more about elementary matrices. So probably I'm going to cover this when I will do that extra review session for the midterm exam. Probably I'll record it sometime this week. I don't know. We'll see. Anyway, now let's talk about properties of determinants. Okay, properties of determinants. So, and I'm not gonna, I'm just gonna go, I'll be straight to the point. And the properties of determinants will be the following. One, very important property that, okay, before I go into that, yeah, if you need that, you have to leave you can leave. Probably it will last around like 15 more minutes, so don't worry about it. You can leave anytime you want. So I won't go more than 1 hour and 20 minutes like the usual lecture. So let if A and B are square matrices of order n, then we have the following important property. The determinant of A times B is nothing else than just the determinant of A times the determinant of B. So this is, so in other words, we call this the determinant is multiplicative. Is multiplicative. Very, very important. So anytime when you have like the product of two matrices and and you want to compute the determinant of that product, is the same as computing the determinant of each matrix, and then you multiply them. Then another property, so this is, let's say this is 1, 2. If I have, let's say, if I want to multiply this by a scalar, we also have that the determinant of a scalar times the matrix A is nothing else than just that scalar to the power, the order of the matrix, which is n times the determinant of A, where C is a scalar. I want to make myself clear, is not a matrix. This is another important property. And I want to point out a remark here. So remark, usually the determinant is not additive. So in other words, the sum of determinants of two matrices usually is not equal with is not usually equal to the determinant of their sum. So in general, the determinant of A plus B is not equal to the determinant of A plus the determinant of B. Of course, you can find some matrices, some special matrices that for which this holds true, but also you can find matrices for which this doesn't hold true. So the determinant is not, so let me say it here, the determinant is not additive. Okay, and you will see that you can take the example from the notes. So if you want to convince yourself, just take this example from the notes. For consider this matrix, two matrices. So A will be 6, 2, 2, and 1, and B will be this matrix 3, 7, 0, and -1. So you compute the determinant of each one of them. For example, the determinant of A will be 2, and the determinant of B is -3. But the determinant of A plus B, if you do the computations, will be nothing else than just -18. So definitely this doesn't hold true. All right. So now I want to talk about, so I'm a little bit in a rush. But anyway, I want to talk about the inverse of a matrix, because the determinant will be related to the inverse of a matrix. So what is the inverse of a matrix? And we have the following theorem. I'm just gonna, we gave the definition last time. We said that what is the inverse of a matrix, but I'm just gonna give you the following theorem, which tells you exactly when we can compute the inverse of a matrix. We say the following: a square matrix. And by the way, this is very important, the word square matrix. A square matrix A, let's say, is invertible. Is invertible, or we also call it non-singular. Non-singular. If and only if and only if, guess what? The determinant is not 0. So that's the theorem. So a matrix is invertible if and only if its determinant is not 0. And let me give you how the question is. We want to answer. So question: how do we compute the inverse of a matrix? Of a matrix. So in other words, is there a formula for this guy? So this is the inverse of a matrix. And in fact, it is. And I'm just gonna give it to you and then I'll explain it. And the formula is the following. The answer is yes. And the formula is the following. A inverse is nothing else than just 1 over the determinant of A times this guy here, which is called the adjugate of a matrix. That's the formula for computing the inverse. So this guy here is called the adjugate of the matrix A. And the question is, how do we compute the adjugate, right? Who is this guy? So the adjugate of a matrix is nothing else than just, remember we've talked about the cofactors. So the adjugate of A, let me just define it, is nothing else than just the cofactor matrix, but transpose. So you take the cofactor C11, C12, but you put them on the column, C11, C1n, then C21, C22, C2n, and you keep going, Cn1, Cn2, Cnn, where Cij are the cofactors, right? So remember, Cij is nothing else than just -1 to the power I plus j times the minor Mij. That was the formula. But you just transpose this. So you put them on a, instead of a rows, you put them on a column. And that's how you compute the inverse of a matrix. So let me give you a quick example. And with this, I will stop here. Anyway, I went a bit faster now. So an example, let me consider this matrix, A to B. Let's say -1, 3, 2, 0, -2, and 1. And the last is 0, 1, 0, -2. The question is, find A inverse. But before even, okay, I want to ask you, before I even answer this question, what I need to make sure of something first. And that something would be that the inverse actually exists. So the question, the first question, does the inverse exist? Because this can be formulated in a tricky way. Actually exist. So what do we need to do? We need to compute the determinant, right? So the determinant of A by computations, and I'll leave it to you as an exercise, will be 3. This is non-zero, so therefore the inverse exists. So yes, the answer is yes, it does exist. Okay, now what do I need to do? Well, I need to compute the adjugate. So the adjugate of A, so what you need to do is you have to compute the cofactors of the matrix A, and then you transpose them. Basically, you compute each row of cofactors, and then you put them on columns. And after you do this, you'll get the following matrix. So it will be 4, 6, 7. Again, I'll leave this to you as an exercise to figure it out. 4, 6, 7, 1, 0, 1, and 2, 3, and 2. And now, the last thing you need to do is that the inverse is nothing else than just 1 over the determinant. So by applying the formula, so finally, A inverse will be 1 over the determinant of A times the adjugate, which in our case will be 1 over 3 here, times this matrix, 4, 6, 7, 1, 0, 1, 2, 3, and 2. Right? And then you can just multiply each one of them, and this will give you, okay, let's do it. It's 4 over 3, 2, 7 over 3, 1/3, 0, 1/3, 2/3, 1, and 2/3. And that's it. That's the inverse. If you want, you can also do by, by writing that, by adjoin the identity, and then you perform elementary operations, you will get the same thing. Anyway, you can do that as well. Okay, guys, thank you very much. I will stop here. Let me just give me 1 second to stop the recording.